Okay, welcome students to this very interesting session. This is session number 46 and we'll discuss about heat treatment processes. These are the contents that I shall try to cover in this particular session. What are heat treatment processes? What is their significance? Then what are the main steps, the common steps during any heat treatment? And then what is the purpose of each step? And finally, we'll take the first heat treatment process for our discussion, a very popularly used process which is called full annealing. We'll try to understand what is the purpose and how do we perform this treatment for hypereutectoid steels, eutectoid steels, or even for hypereutectoid steels. Okay. Now, before I define heat treatment for you, uh, one of the facts which all of us must know is that one of the main reasons why steels are the most important commercial materials in the industry is their good response to majority of the heat treatment processes that are available. So heat treatment plays a very important role, an indispensable role in the wide acceptance of steel as an engineering material. There are very few materials which, like steel, can give good response to virtually all type of heat treatment processes that are available. How is it defined? Heat treatment, you see, I've already said that heat treatment is not a single process. It is a common name that has been given to several processes. Why common name? Because all these different processes, which we'll discuss in the next one or two sessions, have the purpose of improving upon the mechanical properties of the material system to which a particular heat treatment process is being given. And the main common thing is that there are three main steps which are common to all heat treatment processes. So whenever you spell out any heat treatment process, whether that is full annealing, whether that is spheroidization annealing, whether it is recrystallization annealing, homogenization annealing, black box annealing, subcritical annealing, or even normalizing, or even hardening, in every heat treatment process, there are three steps which are common for all processes. Yes, only the magnitude of the temperature values, the magnitude of the cooling rate values, the magnitude of the soaking values that would be kept in every heat treatment process, they are specific and unique to a given heat treatment process. But the steps are common. So heat treatment process is defined as a combination of heating and cooling operations which are timed and applied to a materials system. Why? To bring about phase changes in the material system, essentially when the material system is in the solid state. And why we are doing all this? In order to get desirable mechanical properties. So students, heat treatment, any heat treatment process would 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 involve a combination of first heating followed by cooling. And we have to heat the steel only till a purpose, only till a point when it does not get into the molten state. So whenever heat treatment is being done, the care is that the temperature to which the steel is heated is a temperature in which the steel would always remain only in the solid state. We would never go till the liquidus temperature of the steel or any material system that has been taken. Timed and applied, see, there would be a specific time for which heating would be done. So we'll choose a proper heating rate. Then there would be a proper time for which this steel specimen would be held at this temperature for some period of time, and then the cooling would also be completed in a stipulated period of time because it would be done at a specific cooling rate. And what are we trying to do through this combination of heating and cooling? We are trying to change the microstructure which existed in the material system, because we were not happy with the microstructure, because we were not happy with the properties which were existing in a material system. So if we have to change the mechanical properties of a material system, we have to change its microstructure. Now, there are two main routes how microstructure can be changed. One is alloying, which is a costly affair. The other is a very simple economical process that's called heat treatment. So whether you do alloying to a material system, whether you do heat treatment, what are you basically doing? Because you want a change in the mechanical properties, through these processes you are bringing about a change in the microstructure which would exist in the material system when the material system comes back to the room temperature. And so timed and applied to a specimen to bring about phase changes. So we are trying to change not only the phases, we at times we'll also change the grain size, because we are changing the microstructure when the material system is in the solid state to obtain desirable mechanical properties. Now let us see that in any heat treatment process, what are the three common steps involved. Students, will the first step is called heating, the second step is called holding, and the third step is called cooling. And we will learn about the purpose of each of these steps in the next slide. In the next bullet point, I'll try to give you the names of some of the most commonly used heat treatment processes that we have for metal and alloy systems, through which their mechanical properties can be governed, can be controlled, can be manipulated, can be tailored, right? And these include annealing, and annealing, as I just named, is of 10 or 15 main types. Then we have normalizing, we have hardening, and finally we have a post-treatment to hardening, which is called tempering. Not only these, apart from these, we have special heat treatment processes which are called case hardening or surface heat treatment processes, which would include carburizing, then nitriding, then cyaniding, then carbonitriding, then flame hardening, induction hardening, laser hardening, to name some of those processes. But these processes that I am discussing with you in the next 3 sessions, they are called conventional heat treatment processes. Okay, so now let's talk about the steps which are there in heat treatment. So students, I just said that why are we giving heat treatment? To change the mechanical properties. And what's the governing principle? The governing principle is that if you wish to change the mechanical properties, please change the microstructure, right? And what does microstructure comprise of? Microstructure comprises of mainly the grain size and the phase that are existing within that grain size. So during heating step, the heating step plus the holding step, the next step, that would finalize the type of grain size that would be seen in the microstructure of your material system. So when you have taken a material system at the room temperature, you heat the material system to a stipulated high temperature, a predetermined high temperature, which is referred to as the heat treatment temperature. One of the purposes that we will now, one of the things that would automatically get sorted out is that you will get some specific grain size now in the microstructure of the steel. But the main purpose of heating the steel to this heat treatment temperature is to get some austenite in the steel. Because when I say that properties of a steel depend upon the microstructure, and microstructure mainly contains different types of phases, their volume fraction, their morphology. Who decides that when you are holding a steel specimen in your hand at the room temperature, who decided that what are the phases that are going to be seen in the microstructure of the steel? Students, please remember, you have done it in the triple T diagram and the CCT diagram when we discussed that it's the austenite decomposition that decides that after the cooling is complete and your specimen has come at the room temperature, what phases are going to be seen in it. So basically, when you say that mechanical properties depend upon microstructure, you can now go on to say that microstructure depends upon austenite transformation or decomposition. But when you are doing heat treatment and when you are holding the specimen at the room temperature in your hands, there is no austenite present in the steel components. Austenite is a high temperature phase. So if you want to transform austenite according to the type of microstructure and the mechanical properties that you now intend to bring into the steel specimens, you have to first get austenite in the steel. So it is for this reason that this heating step is done. So during heating of the steel, we will heat the steel to a heat treatment temperature. Depends upon whether you want 100% austenitic structure or whether you want partial austenitic microstructure. If you want 100% austenitic structure, then you will have to heat your steel and you will have to select your heat treatment temperature, which would be beyond the upper critical temperature of the steel. And if you are only interested in partial austenitic structure, because along with austenite, the other phase or phases that are present are actually required in the final microstructure also, then you would not try to eliminate those phases by taking the steel to a temperature when you get 100% austenitic structure. In that case, you would always require a partial austenitic structure. And if that's the case, then you will always take this heat treatment temperature above the lower critical temperature of the steel, but below the upper critical temperature of the steel. So no sooner you go beyond the lower critical temperature of the steel, austenite appears in the microstructure of the steel, but it's still not 100%. So as you go beyond the lower critical temperature, the higher you go, the more is the amount of austenite that keeps on getting formed. But you will not reach the upper critical temperature of the steel, because that would get you into 100% austenitic structure. So I again repeat, the main purpose of heating the steel is to get austenitic structure in the steel, either complete or partial. If 100% austenitic structure is required, the heat treatment temperature would be in excess of the upper critical temperature of the steel. If, however, a partial austenitic structure is required, then it would be after the then it would be somewhere in between the lower and the upper critical temperature of the steel. But also the secondary thing that you are getting due to heating is that you are now trying to achieve some specific austenite grain size also, which would ultimately be seen in the room temperature mic. So the grain size would also get fixed according to this heat treatment temperature, but it would not be finalized, because grain size would be finalized only after the soaking step is complete. So we come to the second step. The second step is called holding the steel at the heat treatment temperature. But students, the main purpose is to obtain chemically homogeneous austenite. Now very quickly, let me tell you that austenite in most of the steels is getting formed from perlitic microstructure. Perlite consists of alternate layers of ferrite and cementite. So as you heat the steel towards the heat treatment temperature, perlite and cementite become unstable because they are low temperature phases. Ferrite starts changing to alpha iron, from alpha iron to gamma iron, and cementite starts getting dissociated. It starts liberating its carbon, which starts traveling towards the freshly formed alpha iron. This freshly formed when this freshly formed gamma iron dissolves the carbon liberated by cementite into it, carbon in gamma iron, you know, is austenite, and this is how austenite begins to form. But it is an experimentally proven fact now that austenite is getting formed through perlite dissolution. Perlite dissolution means that its ferrite and cementite is getting dissolved. Now, experimentally, it has been seen that the dissolution of ferrite and cementite does not complete or does not happen at the same rates. As a result of it, what has happened that when ferrite and cementite dissolution is taking place for the formation of austenite, austenite is continuously getting formed because of dissolution of ferrite and cementite, but the ferrite dissolution completes and cementite dissolution is still incomplete. So the process stops, and as the process stops, you say that whatsoever austenite was to get formed, it has got formed. But the point is that when you reach this, when you have completed the heating to the heat treatment temperature, at the heat treatment temperature, austenite though has got formed, but austenite that gets formed in regions where originally ferrite is there, and austenite that gets formed in regions where originally cementite was there. I'm talking about the perlitic structure, because it's the perlitic structure which is getting transformed to austenite. And in the perlitic structure, what did you have? You had a lamella of ferrite, and then an alternate lamella of cementite, and then an adjacent lamella of ferrite, and again an alternate lamella of cementite. It is these very regions where austenite is getting formed. But because ferrite dissolution is complete and cementite dissolution is still incomplete, in the original perlite structure, wherever cementite lamellas were present, still some cementite, and which is largely carbon, is present. So you say that when I have reached the heat treatment temperature, austenite formation has got completed. But is that austenite completely homogeneous? Please give and try to appreciate that in regions where originally ferrite was present, austenite is containing less carbon over there. And in regions where originally cementite was present, because they are still containing some cementite and carbon, those regions will appear to be containing more carbon in the austenite form. So this austenite is chemically inhomogeneous. And what you need to do, you need to give diffusion sufficient of time so that the diffusion process realizes that, oh my God, there is carbon composition gradient in this austenitic structure that has got formed. And that is what exactly we do by doing this soaking or holding at the heat treatment temperature. The diffusion process activates and it picks carbon from regions of cementite portion and takes them to the deficient ferrite regions. And after a while, that time you know through experience only, 2 minutes, 5 minutes, or even half an hour, you will then see that austenite, which was chemically inhomogeneous over here, becomes chemically homogeneous. So now students, when this heating and holding step is complete, you have completely chemical homogeneous austenitic structure with you, either 100% or whatsoever fraction you had desired for, depending upon your choice of heat treatment temperature. And now this austenite is chemically homogeneous and is completely ready that if it is given cooling and is brought to a temperature lower than the lower critical temperature of the steel, it will start transforming into other phases to give you the room temperature microstructure. And that is what exactly we do in the third step. So in the third step, cooling of the steel at a specific cooling rate is done. And now this cooling rate is done according to the CCT diagram. Students, very slow cooling would give you perlite, intermediate in fast cooling followed by slow cooling who can give you bainite, very rapid cooling more than critical cooling rate would give you martensite. Now you have to see what do you want to form in the final microstructure of the steel according to the properties that you are desiring for by the heat treatment process. And according to that, you follow a cooling pattern for your given steel. So these are the three main steps that are done in heat treatment. First step, heating to form austenite. Second step, soaking to make that austenite chemically homogeneous. And third step, cooling to now decompose or transform that austenite into desirable phases so that a desirable microstructure and hence mechanical properties are obtained in your resulting steel which has gone through the heat treatment process. Now, the first process that we'll discuss here is called full annealing. And let me share what are the different contents for full annealing that we'll discuss with you. We'll discuss what is the purpose of full annealing, what is the procedure, what type of microstructure is obtained after full annealing, and are there any limitations of full annealing. And I'll also very briefly cover that why hypereutectoid steels ideally should not be given full annealing treatment. So, okay, let me again go back and explain to you the purpose of full annealing. Students, please note that whenever you are doing a heat treatment process in which very, very slow cooling rates, which can be called, say, equilibrium cooling rates, are being followed, the process is annealing. So whether you do full annealing or you do isothermal annealing or you do spheroidization annealing or you do black box or subcritical or stress relieving or homogenizing, whatever type of annealing is being done, annealing generally refers that the steel in the third step of heat treatment would be cooled at an extremely slow rate of cooling, equilibrium rate of cooling. Okay, what's the purpose of full annealing? If we talk about the purpose, you see, for any reason, if the steel's microstructure is not okay, means you have very coarse grained structure which is giving you inferior mechanical properties. Suppose uh, steel was subjected to some welding where it was taken to a very, very high temperature, and as it was cooled, a very bad type of a microstructure which is called Widman-Staton structure, coarse grained structure with all pro-eutectoid constituent coming at the grain boundaries and also in the type of a mesh type structure within the grains. The structure is called Widman-Staton structure. and it gives very inferior mechanical properties to the steel. Particularly, it ruins the ductility and the toughness of the steel. So for some reason, if the steel was given a treatment, or when it was being worked, its grains deteriorated and became very coarse grained, or if the steel is not having good softness, steel is not having good ductility, or if the steel has got a lot of internal stresses, residual stresses, or locked in stresses in it, or if for 0.3 to 0.4 carbon steels the machinability is not good, there are various reasons for which full annealing treatment can be given to the steel. And once full annealing treatment has been given to the steel, your steel will have a beautiful grain structure in it. Your steel would have very good toughness. Your steel would have very good ductility. Your steel would have uh, for 0.3 to 0.4 percentage carbon steels, the best machinability would be there in the steels when they are in the full annealed state. And what is the microstructure that you get after full annealing? The microstructure is fine grained structure, means grains are small and fine, but they have coarse lamellar perlitic structure in them. Coarse lamellar, I'll just show you when I come over here what type of microstructure is obtained, right? So, and what's the procedure? Okay, in the next slide, let me show the procedure. You see, it would be different. The procedure would be different whether you are doing this treatment for a hypoeutectoid steel or for a hypereutectoid steel. As I said in the previous slide, that generally for hypereutectoid steels this treatment is not given. But then if somebody asks you that if for some reason it has to be given, how would you give it? So for that also we have tried to cover. So students, we'll take the hypoeutectoid steel sample at the room temperature. We'll heat that steel to a temperature which is more than the upper critical temperature of the steel, 20 to 40 degrees more. You can go anywhere between 20 to 40 degrees in excess of the upper critical temperature. You will hold the steel at this temperature for some period of time. Why? To make the austenite formed as chemically homogeneous. And finally, you'll start doing equilibrium cooling. Now, a question might arise in your mind that how do we achieve such slow rates of cooling? Such students, equilibrium cooling would mean about 15 to 20 degrees centigrade per hour. These are very slow cooling rates. Generally, they can be achieved by switching off the furnace in which the specimens were being heated, and give time. So after 10 or 15 hours, if the say specimen was taken to 900 degrees centigrade, right? And if you are following a cooling rate of say 10 to 15 degrees centigrade per hour, after 9 or 10 hours, your specimens would reach room temperature. But this makes the productivity of the furnace very poor, because the furnace would remain occupied for this long period of time. So what you can do is you can have good heat insulating material containers. You can take out the specimens from here, and very quickly you can transfer to those heat insulating materials. For example, generally the small scale industries which we visit, what do they do? They create a bed on the floor, and that bed on the floor is covered with, or is filled with, good heat insulating materials like ash, limestone, etc. They are very insulating materials. So quickly you pull out the specimens from this furnace and put in that bed, right? And again, the cooling rates that would be achieved by the steel components would be somewhere around 15 to 20 degrees centigrade per hour, or 10 to 15 degrees centigrade per hour. And you with experience would come to know that what's the time, and you can note that time from the CCT diagram, that if I had taken my steel to this temperature, followed this type of a cooling rate, after what amount of time would steel would have been cooled to a temperature below its lower critical temperature. And you know, no transformation takes place during cooling when you are at a temperature lower than the lower critical temperature of the steel. So if beyond this temperature, there is no need of slow cooling. So now you can do air cooling to improve the productivity of your process. In case of hypereutectoid steels, if you take the steel to a temperature more than the upper critical temperature, when we were discussing the iron cementite diagram, and when we were discussing the equilibrium cooling of hypereutectoid steels over there, you know that as you start cooling a hypereutectoid steel, the hypereutectoid steel has got proeutectoid cementite in it. And when this proeutectoid cementite is being subjected to slow cooling, as is the case during full annealing, this entire proeutectoid cementite would deposit itself on the grain boundaries in the form of a very brittle network, which would impair all the mechanical properties of the steel. So there is no need of taking your hypereutectoid steels for full annealing, but even if they have to be given full annealing, take them to a temperature which is above their lower critical temperature. So you'll have a partial austenitic structure over here, homogenize it, and not would it get only homogenized, also when you'll start cooling it, this austenite will transform, and this austenite will transform into coarse lamellar perlite again, in which the cementite particles would have a globular or a spheroidal type of a shape. So you can give full annealing to hypereutectoid steels if you do not wish to give normalizing. But there are no reasons why you cannot give normalizing when you have all the setup to give full annealing. It requires the same setup. So it's better that for hypereutectoid steels, we give normalizing heat treatment. We never full anneal them. Okay. So if you wish to see the type of microstructure that would be obtained in the steel after full annealing treatment has been given, coarse lamellar. See students, in this case, the ferrite lamella is so coarse, so wide. The cementite lamella is also quite thick. So in case of normalizing, what you will observe is that the cooling rate would be air cooling, and it would change to perlite, but it would not be coarse. It would be fine perlite. Fine perlite would only means that the number of lamellas of ferrite and cementite would be thinner and would be much more in number. So in case of coarse perlite, because the ferrite lamella, the cementite lamella are less in number and thereby they are coarse. And if you had been seeing this microstructure for normalizing, there you will note that for the same amount of perlite, 100% perlite, you will see that these lamellas would be much finer, much thinner in width. So let me see if there is any other thing that so limitations of full annealing. It's a very, very slow process. It impairs the productivity. Not only does it impair the productivity because it keeps your furnace occupied, which is lowering the productivity, even the fuel consumption is very, very large because because your furnace was maintained at a temperature say 900, and now for no reason you are bringing it again down to 25 degrees centigrade, and again you'll for the next batch of pieces that have to be heat treated, again from 25 you'll take them to 900. Whereas in normalizing, you'll see the furnace can be kept maintained at the heat treatment temperature. You don't have to reheat it from the room temperature for the subsequent batch of parts which have to be processed. So I think what all was written over here, we have all answered that. And now in the next session, we'll start with another very, very important heat treatment process, which is called normalizing. So students, thank you so much. Thanks for watching, and also thanks for your patience.